Astronomers are re-evaluating their planetary formation models in light of the big planet, which shouldn't exist according to established theories about space. The discovery is remarkable since red dwarfs are estimated to make up around 75% of all stars in the universe, making them the most prevalent type of star. Red dwarfs often have a small number of planets. This is due to the fact that tiny stars shouldn't have sufficient additional material from planet formation to support massive planets. Typically, the mass of the planets identified in the vicinity of red dwarfs ranges from about that of Earth to that of Neptune, but unlike GJ 3512b, they nearly never come close to Jupiter's mass. As a point of comparison, Jupiter has a mass that is around 20 times that of Neptune, and 300 times that of Earth. Because GJ 3512b is such a large fish in a small pond, the researchers claim that, at least by the standards of current theories, the host star shouldn't have had enough material to create the gas giant in the first place. Researchers are now questioning whether gas giant planets truly must begin their lives as developing heavy particle embryos before chowing down on huge amounts of gas through a process called core accretion. The main theory is that if the star GJ 3512 first began its existence surrounded by a very huge disk of gas and dust, the disk's gravity would be powerful enough to cause instabilities inside it. The disk would then directly collapse in some areas, eventually generating massive planets without going through the traditional two-stage development process. This is known as the gravitational disk collapse paradigm, and up until now, it hasn't received much attention in relation to planets orbiting red dwarfs. The main problem with this scenario is that no examples of such huge disks orbiting young red dwarf stars have been discovered yet. However, NASA's studies found that the gravitational collapse hypothesis is the most plausible explanation for how a planet as big as GJ 3512b could have developed around a star so small. The researchers also discovered evidence for a second giant planet located far further out in the system, as well as signs that a third massive planet may have been expelled from the system in the past, which strengthens the argument for gravitational collapse. GJ 3512b is now a spectacular candidate for a planet that might have formed from the instability of a disk surrounding a star with very little mass. This discovery motivates us to evaluate our models. But that planet is not the only thing in space that defies reason. A brand new exoplanet has also been discovered in the nearby constellation of Centauri. It has been given the title B Centauri b since it orbits the B Centauri binary star system. The B Centauri system is the belle of the ball for a few reasons, not least of which is that it orbits a binary system that is collectively somewhere between 6 and 10 times heavier than our Sun, making the B Centauri system the heaviest planet host in known existence. It was first observed by the aptly named Very Large Telescope at the European Southern Observatory, which is located in Chile. B Centauri is now the star system with the hottest planet orbiting it. In fact, it is so hot that scientists previously thought planets couldn't orbit it. B Centauri A, the system's primary star, is a staggering 32,000 degrees Fahrenheit, approximately 3 times hotter than our Sun. Together with its supporting star, this system is radiating the newly discovered planet with enormous amounts of X-ray and ultraviolet radiation. In a statement regarding the finding of B Centauri b, Swedish astronomer Marcus Janssen stated that stars like this are typically seen as highly destructive and deadly environments. Another reason why this little big planet could not exist is that it is 550 times further from its binary star system than Earth, and 14 times farther from Beta Centauri than Pluto is from our Sun. This unusually broad orbit, one of the largest in the known cosmos, may be the reason why the planet has been able to withstand all the radiation from the star pair it calls home. Another feature that distinguishes this new exoplanet is the young age of the stars it circles, which are just 15 million years old compared to our Sun's 4.6 billion. The discovery of this new, somewhat nearby planet is a technical achievement that would have been unimaginable even 30 years ago, when the first exoplanet was discovered. The universe will probably continue to get weirder and larger than ever as big telescopes get more and more sophisticated. Is Alpha Centauri, the nearest star system to our own, home to any livable worlds though? Scientists have been trying to find an answer to this issue for years, but have been unable to look past the two sun-like stars, Alpha Centauri A and B, to detect any indication of circling planets. The planets of Alpha Centauri's system have been sought in several studies, with varied degrees of success. In 2012, astronomers believed they had discovered Alpha Centauri BB, a planet that orbited Alpha Centauri B. However, in 2015, other researchers appeared to rule out the planet's existence. Investigations into Proxima Centauri have been more successful, revealing Proxima B, which may be an Earth-sized planet, as well as Proxima C, which has also been suggested to be a planet. Ptolemy, an old Arabic name for Alpha Centauri, is also known as the Telescope for Orbital Locus Interferometric Monitoring of our astronomical neighborhood. It is a very modest telescope that will be built in 2023 with the aim of searching for planets around Alpha Centauri A and B. The University of Sydney has been conducting lab testing and simulation work on the technologies for Ptolemy, and the group is now working on a full-scale prototype. The technology is essentially ready to launch, even though key components of the mission, including the rocket voyage into space and the station in Earth orbit, still need to be worked out. The primary function of the telescope is to investigate the possibility of planets in each star's habitable zone by taking advantage of the binary nature of Alpha Centauri A and B, which are just slightly further apart than Uranus and the Sun. The telescope will analyze the stars using a diffractive pupil, a new technique that makes use of an optical trick. The 12-centimeter wide telescope will divide the star's light into thousands of pixels instead of capturing extremely high-resolution pictures of them, resulting in a detailed pattern image that will provide a type of photonic fingerprint of each star's location in the sky. The researchers expect to detect minute changes in each star's location, brought on by the gravitational pull of any orbiting planets using this data. Because there are two stars present rather than just one, this astrometric measurement is much easier to perform and allows for more precise calculation of the distance between the two stars. This specific tactic is simply waiting to be used on Alpha Centauri. It almost seems as though the cosmos placed it there specifically for this purpose. The researchers should be able to discern the presence or absence of planets orbiting at a similar distance to Earth, that is, inside the habitable zone of Alpha Centauri A or B, after 2 years of astrometric observations with Ptolemy. However, astronomers can determine the masses of any newly discovered planets using astrometry by measuring the intensity of each planet's gravitational attraction to the stars. The observable distinction between, for example, a gas-shrouded mini-Neptune and a more Earth-like stony orb is blurred by the fact that the majority of other planet detection techniques only produce mass estimates. However, there are a few small drawbacks. Which of the two stars in any such planet's orbit will initially remain a mystery thanks to Ptolemy's research. But if there are any potentially hospitable Earth-mass planets in the system, we would know with almost absolute certainty. We'd be able to detect if it's an Earth-mass planet or a habitable planet. If we find something, we expect that it will spark a little gold rush and prompt more advanced missions to search for it. Two intriguing advancements in exoplanet science are brought forth by the Ptolemy expedition. The first involves doing space science off-world utilizing private funding rather than only backing from space agencies and other state organizations, focusing on a risky venture with little assurance of success. Since there's the possibility that there won't be a planet in the Alpha Centauri system, these kinds of high-risk missions have been very challenging to convince public funding organizations to support. Despite this, the potential rewards are enormous. If there is something, we would be aware that the closest star planet to us may have a planet that's possibly hospitable. It would drastically alter NASA's plans. The research also represents a long-awaited transition from the discovery of thousands of exoplanets over the past 2 decades to the lavishly detailed study of specific star systems. The technology of the Ptolemy telescope is intriguing given how close these stars are to our own. Within a few years, NASA should be able to determine if there are one or more planets that could support life that are close enough for us to send robotic probes across interstellar distances, in addition to using telescopes to observe them. Telamon would offer crucial information in support of such a multi-decadal expedition. Proxima b is the only planet in the system that we are aware of. NASA would probably concentrate on Proxima if we finally determine that Alpha Centauri A and B don't contain habitable planets. We may not have to wait long to find out if everything goes according to plan. That's all we have about planetary discoveries for now. Subscribe to our channel for more exciting content about space exploration. Go through other videos on our channel if you're still curious about the mysteries of the universe. Until next time.